Hi guys, in this video I want to show you how you can use the ULM linker for linking together different object files into an executable. On the website you will find information about how to download and install the ULM linker. If you haven't done that already, you should now pause and first do that so that you can do together with me all these examples in this video. Of course, one reason for doing this video and talking about the linker is also giving you a better understanding about the toolchain that is involved when you use GCC. Even if you translate a single C program into an executable, you have this complex toolchain. You always have the preprocessor, you always have a compiler which just generates assembly code, and this assembly code just gets translated into this object file. And this object file then needs to be linked together with certain libraries so that you actually get an executable. And this is the case even for such a simple C program like this here. And even if I would replace the first line, this include directive, with an explicit declaration, in this case I get rid of the preprocessor. I don't have to talk about the preprocessor, but still a linker is required. And this is kind of obvious because this C program contains a definition for function foo, it contains a definition for function main, but it also uses this function putjar, which is not defined in this C program. The functionality from this putjar function comes from somewhere else, from an external library, and it's not available to the C compiler, it's only available to the linker. Now, in order to talk about what the linker is doing, I first want to talk about a program that can be translated into an executable where no linker is involved. And to overcome this problem, this circular dependency, I want to do the following. I want to manually basically translate this file large.c into some assembly code for the ULM platform, and in this case, when I do this for the ULM platform, I can get rid of this external function putjar, because for the ULM platform I have this instruction which can print a single character. And that means I can have some equivalent, or from a logical point of view, equivalent assembly program to the C program that can be translated just by using the assembler into an executable. And once this is done, we can think about how to split a C program into different pieces that can be translated independent of each other into object files and then linked together, and then show you how you, in a similar fashion, could do this with assembly code. This assembly program can be split also into different translation units that can be translated into object codes, and by that you better understand what this linker is actually doing. So first let's check that this C program is first of all correct and is doing what it's supposed to do. It's printing foo, and now we think about how to translate the C code into assembly by ourselves for the ULM in a way that we do not have any external code, so that we do not need a linker. And for that I already prepared a few things, basically just some EQ directives, so that I can in a more understandable way denote registers used for the stack pointer, for a register for storing the return address, and storing the address of a called function. Now the structure of this assembly program will be the following. In the beginning I have some startup code. Basically the startup code will initialize the stack pointer. It will call function main, because function main is the first function that should be called in the C program, and when function main returns, it should halt the execution of the program, in this case with execute 0. So this code comes later after this comment, and then I need some code for function foo, and also some code for function main. Okay. Let's start with the startup code. First I have to initialize the stack pointer. So now the stack pointer points to the end of the memory. Then I have to call function main. The function call always works according to this pattern. I have to decrement first the stack pointer, in this case by 8, so that this function can store its return address on the stack. And once the function returns, I have to increment it again by the same amount I decremented it before. So in between, I now have to jump to this function. So that means I first have to load the address of the main function into this func call register, and then I have to call jump to this stored address. And here I also leave behind the return address in register return adder. And once this is done, I halt the execution of the program with exit code 0. Okay, and now I could implement function main. The pattern for implementing a function is the following. I begin with a label for this function. In this case, the label is simply main. Then the last instruction will return from the address, and it assumes that the return address is stored in red adder. Now in between, I have to do actually two things. I first have to store as first thing in the function the return address on the stack, so that I can reuse this return adder register, and that means I have to first move the value stored to the stack, and before I return I have to restore the value of this return register. So from the stack I have to copy it back. And in between, I'm doing what this function is supposed to do. I call function foo. And the function call, again, has the pattern. First, I decrement by 8, of course, the stack pointer. Then I would call the function and afterwards increment it. And that means here, in between, I first load, in this case, foo into func call, and then I call this function. And the return address again gets stored in this register. Okay, and now the same thing I do here for foo. I begin with the label. I start with the last instruction so that I do not forget it. Then I recall that I first have to store the return address on the stack, even though this would not be needed in this case because foo is a leaf function, but I want to do it anyway because optimizations are not relevant here. It's relevant that things work ideally always according to the same pattern. So this is the pattern, so storing the return address, restoring it, and jumping back. And in between, I do what this function is supposed to do. I print these characters. Put CF, and here I just change the characters to O. This is also O, and this should be a new line. Okay. And now, if there are no typos, this should be a self-contained program, which is from its logic equivalent to what I described in the C program. And now I use the ULM assembler generated for this instruction set that supports stack operations. And this is doing what it's supposed to do. Okay, and before we now split this assembly code into pieces, let's first have a look at the executable, now generated first from the assembler. So we can simply use cat to look into the machine code. And here actually I don't want to look into the machine code, I actually just want to look here into the symbol table. And you see that we now have a symbol main, which is referring to a location in a text segment, and a symbol foo referring to a text segment. Of course, also other symbols that are used together with the EQ directive. But these two symbols are now of interest. And of interest is also that you have here a lowercase t. The lowercase t indicates that it's a symbol that is ignored by the linker, or you could say invisible to the linker, which is now not relevant because we are not using a linker at all for generating this executable. But let's compare this to the symbols generated by the C compiler. That means I now again use GCC to translate large.c into an executable, and here I cannot use cat to look into the executable, or you do not see useful things. But if you use the command nm, then you can look into the symbol table of this executable. And this might look different on your platform, but on my platform you see that I have here a symbol underscore foo, which is the symbol GCC generated on my platform for this function label foo. So it's always using a underscore first and then the name of the function. And here, so you see the difference is that these symbols are also symbols for the text segment, but this T is an uppercase symbol, which means that's a symbol that is not ignored by the linker, or it's visible to the linker. So this is a minor difference here. Let me also, before I continue here, show you how this might look on your machine. If you are using, for example, Linux, then the symbol table might be larger. I'm using here in this tab GCC on a Linux machine, translated the same way. Look at the symbols, and then you see lots of symbols, lots more, but you also see, for example, here the symbol foo, in this case without an underscore, and here the symbol main. And of course you also can use nm together with grep to search, in your case, for the entry which contains foo, and then you see you can pick out the relevant information. So here main also is uppercase, and here the string also contains main. That's why I'm seeing here two symbols. And this is a minor difference. So, but it will become relevant when we split this assembly code into pieces. Once we split it into pieces, the linker should see certain symbols, in particular the symbols for these functions. Now do the following simple modification. You use the dot global, or actually it's a global directive together with the symbol foo. And this simply tells the assembler to turn the symbol foo into a global symbol, symbol that is visible to the linker. And we also do this here for main. And then we again use the ULM assembler for translating this into an executable first. Here I have the command. And now I look again at the executable, now again generated from the ULM assembler, so it's readable when I use cat. And then you see here, actually it worked as I wanted it. Foo is now a symbol with an uppercase T, and here, because I just copied this line, but I forgot to change this into main. Main is still here denoted with a lowercase t. So what we are doing here becomes clearer when we in the end use the linker. But now first make sure that both symbols main and foo have uppercase T once you use here in your code at someplace main. Actually, it doesn't matter whether you use it before declaring this label. You also could declare it here. Should have the same effect. Just check it. the location for this global directive is not relevant, but usually you would do the following. I also can explain you how this is related to a C program. In C, you know that we have this specifiers static. If I would declare foo as a static function, and now again use GCC to translate it into an executable, and look at the symbol table, then foo or underscore foo would also be a symbol which is invisible or ignored by the linker. So basically the rule of thumb would be the following. If you have some function in C which is static, then you do not use a global directive. And if it's a non-static function, then you use the global function. So in C, by default, everything is global. And if you want to have something not global or local, you would skip the static. Now for the C program, it might make sense to split this into two source files, into a source file foo.c, which just contains the implementation of function foo, of course also the declaration for function putchar, and another translation unit for function main. And then you can translate both of these source files independent of each other into object files. You know that the object file can be generated with GCC by using the option -c. I will also show you this again in the video. That means you can just generate this file main.o. Then you also use GCC together with option -c to translate foo.c into foo.o. And then you can use afterwards the linker. In this case, you also can use GCC as a wrapper for using the linker to link together this object files, but also this library into one executable. Now let's do this first with C, and then of course it's kind of unclear what these libraries actually do contain, but afterwards when we do this for the assembler program, it becomes clearer, because then we don't have to deal with these external libraries. Okay, now for splitting large.c into different translation units, I first make a copy of it, call this copy main.c, and another copy of it, which I call foo.c. And from these copies, I simply remove certain parts. For example, main.c is supposed to only contain the implementation of function main. Still, I need a declaration for function foo, so that the compiler doesn't give me a warning for using undeclared functions. So I end up with that. It just contains the declaration of function main and this bookkeeping information that function foo is not expecting any parameters, doesn't return a value. That's it. And in foo.c, I simply remove the implementation of function main. So everything below this line here gets deleted. Now I have two separate source files, which I can translate into machine code separately. With the option -c, I can first translate main.c into an object file, which now contains machine code, which is not executable. You can use object dump -d for debug main.o. That's the file that was created, and then you see these are basically the machine instructions in this object file. And in the same way, I can translate foo.c into foo.o. So also this here now contains machine instructions. And these two object files I now can link together. For that I use GCC as a wrapper for the linker. And this linker gets main.o and foo.o. And it generates a.out from that. So to actually see that this a.out is new, let's first remove it, generate it again. That's it. And if you would modify code here, for example, I now just have to translate foo.c into an object file. And then I have to link this object file foo.o together with main.o. Main.o is unchanged because I haven't modified the source file, so I didn't have to regenerate the object file. I can link it together, and now I can do here some work, and this changes here only require me to translate this source file into a new object file, and then I can link it together with object files that can be reused because the corresponding source file was not changed. So this is how it works for the C programming part. The assembly code I now can split in a very similar way. I can generate one source file that just contains the code for function foo. Maybe it also contains the EQ directive so that I don't have to modify the code in here. Another source file will contain all the code for function main, and then actually a third assembly source file will contain all this code for initializing the stack and for jumping to function main. And the linker needs to know that this code for initializing the stack and so on needs to be called first when this executable gets actually executed. And by convention, you indicate that by using this symbol _start, which has to be global. The linker knows that the first instruction following this symbol is the first instruction that should be executed when this program gets executed. So I will show you how I split this assembly code into these three parts, and then I will also show you how you can now, instead of just translating one large assembly code, do this in independent steps. You first can translate main.s into an object file, and object file means it's machine code that is not executable because it's missing certain things. Then you also can translate foo.s into an object file by using the assembler, and also this assembly file start.s. And then you can link together this object files into one executable by using the ULM linker. And of course, the advantage would now be, if this would be really large assembly files, if you make one modification for in foo.s, you just have to regenerate the object file. You have to use the assembler to generate a new object file, and then you can link together the new object file with the old object files. The old object files are still good enough because the assembly code wasn't changed, for example. And this is what I show you next. Splitting this file large.s into different translation units, I do basically the same thing. I first make a few copies of it. One copy is called main.s, another one is called foo.s. So it's clear main.s contains, or is supposed to contain, just function main, foo.s just function foo. But here I need a third copy for all this platform dependent code for initializing the stack pointer and somehow calling function main, so that it seems as if function main is the first thing that gets executed. Now in main.s, now I have to remove basically the startup code, so everything from here to here. And I still need this EQ directives actually in all three copies in general. And in foo.s, I have to remove the startup code. So everything from up to here, or down to here, and everything after function foo. So everything from here to the end of the file should get deleted. And then this startup code actually becomes some platform dependent function. And that means I first of all have to delete everything after the startup code. And I have to turn it into a simple function, a function that only gets called but never returns. So here I don't have to do things like decrementing the stack pointer, which would not make sense anyway, because here the stack gets initialized and we do not return in the end. The name for the label by convention has to be _start. And because the linker has to deal with this label, it should be a global label. Okay, like that. And now I can translate first main.s into main.o using the ULM assembler. And if I would invoke the assembler like that, the output would be called a.out for assembler output. But you see here this assembler output just contains code generated from main.s. And now on the command line, I could change this, move a.out into main.o. But it's simpler to use simply the option -o for specifying the output file. -o main.o should be generated from main.s. And then main.o is basically the same thing. You have here code generated from main.s. And you have here undefined symbols. For example, foo is undefined because we are using foo here in the function call, but it's not defined anywhere. And now in the similar way, we generate foo.o from foo.s and start.o from start.s. And of course, you're encouraged to look into this object codes so that you see here is only machine code generated from here. And this start.o just contains machine code generated from here. And now I can use the ULM linker, ULM LD, to combine the object file main.o with start.o and foo.o. Now, the order is not relevant. The linker will, as you will see, add some code that first jumps to function start and hopes that function start is well implemented so that function start does all this platform dependent things like initializing the stack and jumps to function main. And the generated file is a.out. And if you look into this file, you see that you have here, for example, a comment that this was generated by ULM LD. And you also see here this magic first line, which makes this actually executable in a way that you now just have to type in a.out, or in my case /a.out, because the current directory is not in my path variable. And now you can do again the same experiments, for example changing here this into uppercase. Now I just translate foo.s into foo.o with the ULM assembler and link again together this object files into an executable, and this new executable now prints foo all in uppercase. Now the advantage of having a linker is that we can split large assembly programs into more manageable translation units. Later you might want to use one translation unit for having code that prints a string, for example. Function put_s could be implemented in one translation unit. A function for printing an integer in another translation unit. And another translation unit could contain a function for reading in an integer. And then you have more manageable code because each translation unit is just realizing, for example, just one function. And then you don't have to copy paste code from a previous project into your new project. But of course, this also comes with a price. If you have many translation units, then you have to keep track of certain things. For example, what object file needs to be regenerated when you modify one of these source files? Do you have to relink object files so that the executable is up to date? But this, of course, can be handled by using makefiles but this is something that we do in a different upcoming session. For now, it's important that you understand how a linker works in principle and that you also do a few examples, a few experiments with this linker.